Hello students, today I discuss about relation between specific heats at constant volume and pressure. So these are represented by Cp and Cv. So we just establish the relation between the specific heats at constant volume and pressure. So first we assume that for n mole of ideal gas, heat is applied at constant volume. For constant volume, if we take n mole of ideal gas and if we apply heat to change the temperature of the gas from T1 Kelvin to T2 Kelvin, then if we take the Cv is the specific heat at constant volume, then the applied heat, we know that by the definition of specific heat, that Q1 is equal to the this is the applied heat. Q1 is equal to n mole multiply Cv multiply the temperature difference T2 minus T1. So here due to the constant volume, we have taken constant volume, so dV is equal to 0. So here no work is done, since no volume change, so no external work is done by the gas. So just we due to the applied heat and due to the change in the temperature, just the internal energy will increase. So the internal energy, if we consider for T1 temperature, if the internal energy of the gas is E1, and for the temperature T2 the internal energy is U2, then by the first law of thermodynamics, since the work done is 0, we will get that the applied heat NCV T2 minus T1 is equal to increase in internal energy E2 minus E1. We will now is mark it this by equation 1. Now for the second case, at constant pressure, here if the applied heat is same at constant pressure, to increase the temperature difference also is the same, T1 from T1 to T2, then here the applied heat will be Q2 N Cp T2 minus T1. This is the specific heat at constant pressure. So this is the applied heat, and this will come from the definition of specific heat at constant pressure. Now here due to the change in volume, here pressure is constant, volume is not, so here volume will be changed, volume will change. So we will take the constant pressure P and the volume difference is dV, then the work done by the gas is P multiply dV. It is also established P multiply dV, the work done by the gas. So the change in the internal energy is same also as previous, because the internal energy temperature difference is T2 minus T1, so the internal energy change will also be same. So this will be U2 minus U1. So here work done we have already obtained P multiply dV. So here by first law of thermodynamics, applied heat NCP T2 minus T1 is equal to increase in internal energy and work done PdV U2 minus U1. So if we replace by equation 1, we know that U2 increase in internal energy is equal to NCV T2 minus T1. If we replace it, then we will get NCP T2 minus T1 is equal to NCV T2 minus T1 plus PdV. So if we rearrange this equation, we will get NCP minus T2 minus T1 is equal to PdV. So we will denote it equation 2. But we know that for n mole of ideal gas, this is a well established relation for a ideal gas, PV is equal to nRT. So here for that, if we take V1 is the volume at temperature T1 and V2 is the volume at temperature T2 at a constant under the constant pressure P, such that V2 minus V1 is equal to dV. V2 minus V1 is equal to dV in this way. So we can write down PV1 is equal to nRT1 and PV2 is equal to nRT2. So this can be written down. So if we subtract equation 2 minus equation 1, then we will get this PV2 minus V1 nRT2 minus T1. So this will be PdV equal to nRT2 minus T1. So if we again replace this in equation 2, so we can write down NCP minus CV T2 minus T1 is equal to N R T2 minus T1. So if we cancel same numbers in both sides, then we will get Cp minus Cv is equal to R. So this is the relation between the specific heats at constant pressure and at constant volume. So their difference is equal to the ideal gas constant. So ideal gas constant is equal to Cp minus Cv. So if you like this videos, then like, share it with your friends, and if you have any question, then comment me.